Hello. Today we are talking about definite integrals. And we've already studied definite integrals in class, and we know that that's the area between a curve and the x-axis. And we've estimated this area several ways. One way was we counted squares. And we did this when we were given a grid and a curve, and we could estimate how many squares we had to estimate the area under the curve. The next way that we learned was a little more specific, and we got much better estimates, and that was by using trapezoids. And we would just break our little region up into trapezoids, find the area of each trapezoid, and add them up. The last method was Riemann sums, and the Riemann sums were rectangles, so we broke our area up into rectangles, found the area of each rectangle, and added those up. So now we're actually going to find this exactly. We're no longer finding an estimate, we are actually going to find the area under a curve, and we're going to use antiderivatives to do that. So this notation that's written right here is read as the definite integral of f of x from x equals a to x equals b. So that's what this notation means. So let's look at a graph. What the heck does this actually look like? So if I just had some curve drawn, and I had A was an x value where I started, B was an x value where I ended, then it would be this area right here. So this is the integral from A to B of f of x dx is going to be the area represented here. So it will be a number. Now, how do we evaluate this integral? So key to this notation is capital F of f is going to be the antiderivative of little f of x. So in other words, capital F prime would be equal to little f. Okay, so what I'm going to do is I'm going to find the antiderivative of little f, which is my capital F. Then I'm going to plug in the upper bound as x into my function. And then I'm going to plug in the lower bound as x into my function. And then I'm going to subtract these two numbers. So let's go ahead and do this example. Evaluate the definite integral from 1 to 5 of x squared dx. So first thing I need to do is find the antiderivative of x squared. So I'm going to evaluate that part. And that's going to be x cubed divided by 3 is the antiderivative of that. Now, technically there's a plus c, and I'm going to go ahead and write this little plus c right here so we can discuss what happens. Now, the notation to say I've taken my antiderivative already, because we know that this integral symbol means antiderivative. Take the integral means take the antiderivative. We put this solid straight line at the end, and we put our bounds here. So that means that I've taken my antiderivative, I still need to plug in my bounds, and I need to subtract. So at this point, I'm going to have, I plug in my upper bound, which is 5, and then I'm going to subtract when I plug in my lower bound, which is 1. Now, if you don't have a calculator, you might want to grab it. You're definitely going to need it later on anyway. 5 cubed is 125. And then I'm going to subtract 1/3. Sorry, I didn't distribute my negative, so I really have subtract 1/3 minus c. And why I wanted us to write this plus c in here was to figure out, well, what happens with these plus c's? And here I have a plus c, and here I have a minus c. So those are going to cancel each other out. That's going to happen every single time. So typically speaking, we don't write this with a definite integral. You don't have to write it. If it's not a definite integral, then you have to have your plus c there. Okay, so now we're going to finish this out, and we have 124 divided by 3. Now, What we do also need to talk about is the fact that integrals are signed. What I mean by that is they will be positive or negative. So for this particular problem, if I were to draw a basic sketch of what's going on here, we have a parabola, and we were finding the area starting at my lower bound, 1, and going to 5, my upper bound. And I'm finding this area in here. So this area is going to be positive, and let me explain why this area is going to be positive. Two reasons: it's above the curve, it's above the x-axis, but the second reason is about the bounds. If I talk about my change in x, I'm going from here to here, my change in x is positive. And then if you think about the y values every single time, my y value is always positive. And because I'm finding an area, ultimately I'm multiplying f of x times dx, which is what I have right here. And because I'm taking a positive times a positive, I will also get a positive. Moving on to the next page. Exploration 5.7a. So this is really talking about the properties of this sign and an even and odd concept for definite integrals. So we're looking at problem number 1. We've got this function graphed, and it wants us to explain, why is this an even function? Well, graphically, it's an even function because it's symmetric about the y-axis. I'm also clued in by the exponent for my variable, and it is even. So I also look at the degree. Now, that does not mean that every function where it has a degree of 2 will be symmetric about the y-axis and therefore will be even, but the degree kind of clues me in. But basically what it means is if I plug in f of x, that's the same as if I plug in negative x into f, I'll get the same value. So in number 2, it says, okay, let's evaluate these two things. So the first one I'm evaluating is the definite integral from negative 3 to positive 3. Sorry, negative 3 to positive 3 of 19 minus x squared dx. So let's evaluate that. First thing I need to do is find the antiderivative. The antiderivative of 19 is 19x, and the antiderivative of x squared is x cubed over 3. I have my solid line indicating I've taken my antiderivative, but I have not plugged in my bounds, and then I write down my bounds. For this one, I'm going to plug in the 3, and I'm going to plug in the negative 3, and then I'm going to subtract. And I'm really going to run out of room here. So I have 19 times 3 minus 3 cubed over 3 minus 19 times negative 3 minus negative 3 cubed over 3. That's a cubed. And when I evaluate this further, I get 57 minus 9 minus negative 57 plus 9. And if I simplify that a little bit more, I end up with 48 plus 48, which is 96. So this first definite integral is 96. Now I'm going to run out of room, so I'm going to erase part of what I have here, and I'm going to move on and do the next one. So now I need to do the definite integral from 0 to 3. Right now what I'd like you to do is make a guess. We've done the definite integral from negative 3 to positive 3 of 19 minus x squared. We should, based on that information and the fact that it's even, we should have a good guess as to what the definite integral will be from 0 to 3 of 19 minus x squared dx. So let's go ahead and work this one out. So now I'm starting from 0 and going to 3 of 19 minus x squared. The antiderivative is the same, so 19x minus x cubed to the third, and I'm going now from 0 to 3. So I'm going to plug that information in. I have 19 times 3. I feel like I've done this before. Minus 3 over 3 divided by 3 cubed, excuse me, divided by 3. Plug in a 0, and I just get a 0 because 19 times 0 is 0, and 0 cubed is 0. So that's going to give me my same numbers that I've been working with, 57 minus 9, which is 48. And how are these two values related? Well, 48 is exactly half of 96, or twice 48 is 96. So why is that the case? Well, that is the case because we are even. That means that this green area is equal to this blue area. Those areas are going to be equal. If I'm even, I'm symmetric at the y-axis, the area on the right of the y-axis will be equal to the area on the left of the y-axis, which is a really cool feature because the second definite integral that I did was much easier than the first one because I didn't have as much arithmetic that I was doing. So if I know from 0 to 3, this definite integral is 48, therefore I would know from negative 3 to 3, the definite integral would be 96. Now, again, this is only for even functions. This does not work for anything else. Even functions only. So moving on to number 3. Now we have x cubed, and explain why this is odd. We have a couple of reasons. Graphically, it's symmetric about the origin. It has point symmetry, which simply means if you were to take your paper right now and flip it all the way upside down, rotate it 180 degrees, the graph would look exactly the same. So it's symmetric about the about the origin. We also know about the degree. The degree for this one is the third degree, which is an odd number. Not all third degree functions are odd. And finally, we know that if I take f of x, that's going to be equal to the opposite sign of f of negative x. So those are all the reasons why I know that this is odd. So looking at this, we're going to use the fundamental theorem to calculate the definite integral from negative 4 to 4 of x cubed dx. So let's go ahead and find our antiderivative. Antiderivative will be x raised to the fourth divided by 4. Straight up and down line to indicate that I have not plugged in my bounds yet. So I plug in the top bound, 4 raised to the fourth divided by 4. Subtract, I plug in the lower bound, negative 4 to the fourth divided by 4. So I go to work simplifying this, and 4 to the fourth divided by 4 is really just 4 cubed, which is 64, minus negative 4 to the fourth divided by 4 is 64, and 64 minus 64 is 0. So again, this is getting back to this concept of a signed area. And I'm going to erase what I've written so I can look at my graph. This area ended up being a positive 64. It's positive 64. And again, my dx is positive, my y value is positive. However, this area down here was a negative 64. So when I take the definite integral from negative 4 to 4, those two signed areas cancel each other out. So my negative 64 added with a positive 64 gives me nothing. So again, this is only for an odd function that is actually symmetric about the origin. This doesn't work for everything. Moving on to number 5. In number 5, we have that the graph here, h of x, is shown. Use the fundamental theorem of calculus to evaluate these two definite integrals. So the first one, 1 to 3. Again, I'm taking an antiderivative, and I'm looking up here. So that's 0.4. My constant stays. X is raised to the fourth divided by 4. Minus my constant 3 stays. X to the third divided by 3. Plus 5x squared divided by 2 plus 5x. Straight line, vertical line to indicate I have not taken the antiderivative yet, and then I have my bounds. So I'm going to plug this in, and at this point I would just use my calculator and just figure out what this is. When I worked this out, I got 2.025 for the first term, minus 27 plus 45 plus 15, and then subtracting, when I plug in a 1 now for x, I get 0.1 minus 1 plus 5 plus 5. And when I evaluated that, I got 35.025 for when I plugged in 3 for x, subtract 9.1 is what I got when I plugged in 1 for x, and then I got 25.925. At this point, it is important that you pause the video and you make sure that my answers are right, or make sure your answers are right, whichever way you want to look at it. But pause the video right now and make sure you understand where all of that came from, okay? Because writing it down is not important. Understanding what you're doing is. So I have one definite integral. So I'm going to go ahead and just write it down up here. So the integral from 1 to 3 of h of x dx is 25.925. Now I'm going to evaluate the second one. The second one was from 3 to 6 of h of x dx. Well, I've already got my antiderivative. 0.1 x to the fourth minus x cubed plus 5 halves x squared plus 5x. And a straight line to indicate I have not taken my antiderivative. Now I already knew what when I plug in 6, sorry, I don't know what that is, so I need to work that out. 129.6 minus 216 plus 180 plus 30. And then I take away what I got from when I plugged in 3. Well, I already found that. That's this right here. Minus 35.025. And that gives me 88.575. Okay, so at this point, I realized that I had made a mistake in my arithmetic. So I'm going to go ahead and fix my answers. And so momentarily, the right answers will be up. Ta-da! Sorry, these are the right answers. So for the first definite integral, we should have gotten 12. And for the second definite integral, we should have gotten 15. You might want to pause the video now to try and figure out if yours is correct. So hopefully you didn't just blindly copy mine. Next, number 6, quick, calculate the definite integral from 1 to 6 of h of x dx. Okay, so I know the definite integral from 1 to 3 of h of x dx was 12, and I know the definite integral from 3 to 6 of h of x dx was equal to 15, which means if I want to go all the way from 1 to 6, I take the area from 1 to 3, and I add it to the area from 3 to 6. So that will give me a total of 27. We're going to use this idea in number 7. So now we have a couple of definite integrals that were given to us. From 2 to 7 for u of x is 29, and then from 2 to 7 of v of x is 13, and then from 2 to 4 of v of x is 8. So let's look at part A. Part A, we want to evaluate the definite integral from 2 to 7 of u of x plus v of x. Well, that's the same as the definite integral from 2 to 7 of u of x plus the definite integral from 2 to 7 of v of x. So all I need to do is add the two definite integrals that I knew, which was 29 and 13, and that gives me 42. Hopefully, let me know if that's wrong. Part B, we're going from 4 to 7 of v of x. Okay, well, this is what I know about v of x. I know from 7 to 2 is 13, and I know from 2 to 4 is 8, and I want to know from 4 to 7. So if I take the big area, which starts at 2 and goes to 7, and I subtract out the area that I don't want the area from 2 to 4. I want the area only from 4 to 7. But if I subtract those two, I should get the area from 4 to 7, which is 5. Exploration 5.8. We're not going to do all of this. I just want to get the basic understanding of what's going on when we're doing a definite integral. So in 1, 2, and 3, it talks about very specifically what it is we're trying to do. And basically what we're trying to do here is we're picking a point T and we're trying to draw ourselves a little strip, so to speak. Eventually we're going to call this little strip a rectangle, and that's going to help us to evaluate some other things. But this is our little strip, or rectangle, whatever you want to call that. And basically I want to talk about the width, and the width of my rectangle is the change in time, or dt. The height of my rectangle is just the function value at t. So if I wanted to find the area of that little strip, that area is going to be my height, v of t, times my width, which is dt. Now that should look very familiar, very familiar. We have a function times dt. So that if I could add up all the rectangles and make the rectangle smaller and smaller and smaller and smaller and smaller, that would give me the area under the curve. So that's what it's talking about in number 4. Write a Riemann sum that will represent the total distance that the spaceship goes. Well, the summation notation, that's my sigma, that's summation notation. I want to start at t is 0 and I want to go to t is 100, and I want to find all of these areas. That's basically really what I want to do. Now, what this is actually going to be, I'm not going to talk about this upper and lower sum, but I'm going to talk about that if I had the limit as my change in t was trying to go to 0 of this sum. So my rectangles are getting smaller and smaller and smaller and smaller. That would be the definite integral from 0 to 100 of v of t dt. And what's important about that is this concept of a definite integral is also the concept of an accumulator. Just like an accumulation of snow, it's adding and adding and adding and adding. It's adding areas together. Okay, so it is actually an accumulator, and that's what we need to think about the definite integral as. It is an area, but it's also an accumulator. We could go on and do these problems, which you are welcome to do. What I will do is I will provide you with my solutions to these, but all it is working with the definite integrals. So you're welcome to do that right now. If you're going to do that, press pause. If you have no interest in doing that, then you're finished with your video. And I highly suggest you give it a go. So go ahead and pause the video and work out 6, 7, and 8. So here are my solutions for 6, 7, and 8. For number 6, my answer is the distance traveled by the spaceship was 773,218.0084 feet. In number 7, the time that this happens is at 1,304.7277 seconds. I know the directions said to the nearest second, but I would use the whole thing. In number 8, I stored that value so that I could do the definite integral, and I got that the spaceship travels 228,979,711.3 feet. And in number 9, I did talk about this. This thing on the bottom that I've circled in blue, this isn't accumulating area. It's just adding up lengths, y plus y plus y plus y plus y. However, what I've circled in red, f of x dx, is accumulating area because I'm taking a width times a length and accumulating those. So if you did not get number 8, I would pause the video here so that you can work with my solution and make sure that you understand it. If you did not get 6 or 7, I would pause the video here to make sure that you understand my solution, to make sure you understand it. I apologize for the length of this video. Thank you for watching, and I hope you have a wonderful evening.